What's up, boys and girls and everyone else? So welcome again to another science video lesson. And then in this video lesson, we will going to draw. Yes, that's right, we will going to draw. And the topic that we will going to discuss today in this video lesson is the ray diagram for mirrors and lenses. So what are the step-by-step process in doing this ray diagram? So stay a while and listen, guys, as we discuss the ray diagram in this video lesson. Okay, so here we are in our video lesson. So we have it right here, the ray diagram for mirrors and lenses. So in our video lesson today, we will going to draw. So you might want to prepare a wrapping paper, ruler, protractor, and a compass for this one. Okay, so now you can pause the video. All right, so you can pause the video every time that we will have a ray diagram that we would like to draw, so that you will be able to follow the step-by-step process in making the ray diagram, and be sure that you will be able to learn everything that we have right here in this video lesson. All right, so with that, let's get started. Alright, so in our previous lesson, we have encountered this law, this statement that we have right here, this principle. This is the law of reflection. Alright, so what does the law of reflection is all about? Law of reflection says that the angle of incidence is equal to the angle of reflection. Alright, so the angle of incidence is equal to the angle of reflection. Now, as we look at the figure right here, okay, as we look at the figure right here, so the incident ray and the reflected ray are all part of your reflection process. Okay, so according to this statement, that the angle of incidence is equal to the angle of reflection with respect to the normal line that we have right here. Okay, so as you can see, if the angle of incidence is 20 degrees, then the reflected ray should be 20 degrees. Then this particular statement works on flat or plane surfaces, like the one that we have right here, the plane mirror. All right. So the angles are measured perpendicular to the surface, which is called the normal line. Okay, so that is the law of reflection. So that was discussed in our previous video lesson. So just click the link above, all right, to watch it again, so that you will have a refreshed, you will still be able to be refreshed with the ideas about this law of reflection. All right, so we have here the plane mirror. Okay, so we have here the plane mirror. So also there is a video lesson that I have created, okay, for this one last time. So just click the link above for this video lesson. All right, so the plane mirror. So suppose we had a flat plane mirror mounted vertically, the one that we have right here, and a candle is placed 10 cm in front of the mirror. Where is the image of the candle located? Okay, so is it A, same side as the object? Is it B, on the surface of the mirror? Or is it letter C, behind the mirror? Okay, so where do you think the image on the mirror, on the plane mirror, will likely to be seen? Alright, so the answer is letter C, which is behind the mirror. Okay, so that is behind the mirror. Now, how about the distance? Okay, how about the distance? So if the distance of the object in front of the mirror is 10 cm, now what is the distance of the image? So as we agreed on our previous lesson that we had, so the distance of the object is equal to the distance of the image in a plane mirror. So it should be 10 cm as well. Alright, not only the distance but also the height of the object. If the height of the object is 5 cm in front of the plane mirror, the image also that is produced by the plane mirror is also 5 centimeters. It is the same. Alright, so that is the plane mirror. So we have here the virtual image that we have encountered in our previous video lesson about virtual image and real images. Alright, so there's no such thing as behind the mirror. This is only created, alright, this is only created when our eyes are tricked, okay, by these reflected rays that is coming from the plane mirror itself. Alright, so that is the virtual image. So basically, what is a virtual image? Virtual image are images that cannot be projected onto the screen. So please do take note that one. And also, the virtual image appears on the opposite side of the mirror relative to the object. Alright, so it appears on the opposite side of the mirror relative to the object. So, okay. So not only that, the images produced by the plane mirror is laterally reversed. If you raise your left hand in a plane mirror, if you raise your left hand, then the image will raise its right hand. Okay, so to further give you an idea what is a virtual image in real life, so this is how it looks like. Alright, so the virtual image looks like this. Alright, so what we have right here is the virtual image, alright, of your mirror. So as you can see right here, that's the object. Okay. That's the object right here. We have the candle. And as I've said earlier, the images that is produced virtually, the images that are produced virtually cannot be projected to the screen. Alright, so cannot be projected to the screen. Again, we replay this one back. As you can see, the image is upright. The image is upright, the same as your object over here. It is upright. So therefore, that this is an example of a virtual image. Alright, so let's go back. Okay, so that is the virtual image. Alright, so next one is the real image. So what is a real image? Real images are the images that can be projected to the screen. And not only that, real images are images that form or that is formed on the same side of the object. Alright? The same side on the mirror of the mirror as the object or relative to the object. So that is the real images. So how does the real image form? Because the intersection of the light rays that you have right here happens in front of the mirror or lens. All right, so it happens in front of the mirror or lens, so something like this one. So the image is somehow inverted. Okay, so the image is somehow inverted, and at the same time, this is a real image. Okay, so let's take a look at the real image in real life. Alright, so let's have this video. This is what the real image looks like. Okay, again, that's the object. And what we used right here is an optical device called lens. Right, so that is a lens. And as you can see right there, the image. Alright, so the image that you have right here is inverted relative to the object. Okay, relative to the object that we used. Okay, so that is inverted. Okay, what is the good thing about real images? Okay, is that when you project it on the screen, like what I'm doing right here, it can be projected onto the screen. So the image that you see here on this paper, or which would be the screen, is the image of the inverted candle. Okay, it's the image of the inverted candle. So this is for the lens. Okay, so there you have it. Go. You can adjust the projected projection screen. Okay. Now let's take a look at the image in a concave mirror. So the real image in a concave mirror. Okay, so this is the image in a concave mirror. So that is a concave mirror right there. Okay, so the concave mirror is a type of mirror which is okay. It's a type of mirror that goes inside. All right, so the curve goes inside. And if you take a closer look on the image on this concave mirror, so that is a real image. So the image that was focused on this projection screen is a real image. All right. So if we will replay this one, so that is the inverted image. Okay, so that inverted image that you have right there is a real image. Again, it can be projected onto the screen. All right. So that was All right, so that was the real image. Okay, in actual. All right, so in actual. Okay, what if the mirror isn't flat? Okay, what will happen to the image if the mirror isn't flat? Okay, so what we have right here is a curved or spherical mirror. Okay, so basically speaking, okay, if you have a spoon, all right, if you have a shiny spoon, so you just get that one and place, all right, so look at yourself on the spoon on both sides, one on the convex side and one on the concave side. So you will notice that there is a difference between the image form on both sides. All right, so what are those? So those, okay, the part of your spoon in which you looked at is called the spherical mirrors. All right, they are called spherical mirrors. So there are two kinds of spherical mirrors. So we have concave and convex mirror. All right, so we have concave and convex mirror. So the convex mirror is the one that is curved outside. All right, and the concave ones are the one that is curved inside. Okay, so convex mirror are also known diverging mirror because it diverges light. All right, this mirror is said to be they diverge light, and the concave one is doing the opposite. It converge light in the process. Okay, so how does they diverge and converge light? So, okay, we will have that one in the ray diagram later. All right, so in a concave mirror, okay, so in a concave mirror, there is one point. All right, there's one fixed point in your concave mirror where your light, okay, where your light, which is going parallel to the principal axis that we have right here, okay, and going directly to the surface of the mirror, this parallel light rays that you have right here always goes to one point. All right, and that point is the fixed point of the spherical mirror, which is called the focal point. This one over here. Okay, so that is a focal point. Okay, so this is where all the light is being converged. All right, if the light comes from the infinity, okay, comes from infinity. So this is where the light will consolidate. Okay, so what are the typical parts, okay, of a spherical mirror? All right, not only the spherical mirror, it has the same, or the lens also has the same parts. They share the same parts together with the spherical mirror, but it is somehow completely different from some other aspect. All right, so these are the parts that you should take note of, okay, when you are making a ray diagram. So the first one, the parts of this mirror or lens that we have. Okay, so this is the lens or the mirror. In this case, we have the mirror, and this is the reflective side. If this is a concave mirror, this is the reflective side. If this is a convex mirror, will be the reflective side of the convex mirror. All right, so this will be the reflective side. All right, next one. We have right here the focal length. So what do we have? What do we mean by the focal length? Focal length is the distance between the surface of the mirror or the pole. We call this one a pole. Right? So this is the distance between the pole and to the focus. Okay, we called it focal length. Then we have the focus. Okay, we have the focus, and the focus is half the distance of your center of curvature. Now, what is the center of curvature? This is the center of your circle. All right, if you use a compass to make a circle, this is the needle part of your compass. Right, the center of curvature is the needle part of your compass. And the pencil, which used to draw the circle, is the one that gives the impression of this arc that you have right here. Okay, the impression of the arc that you have right here is the pencil on your compass, which is the circumference. All right, the one that draws the circumference of the circle. All right, now, again, the focus is the distance half of your center of curvature. Okay, now what is the center of curvature? This is twice the distance of your, okay, this is twice the distance of your focus. Based on its formula, that is 2f. Alright, so that is 2f, so twice the distance. Okay, so focal point or focus is center of curvature over 2. Okay, half the distance of your center of curvature. So I'll just give you some example here. If your center of curvature is 10 centimeter, If your center of curvature is 10 centimeter, what will be the focus? So, following this formula, it will give you 5 centimeter. Alright, so that's the key thing there. Alright, so that is the center of curvature and focus, and both of them lies on a certain plane called principal axis. Okay, the principal axis is an imaginary line that goes through the middle of your mirror. Alright, so the middle of the mirror. So that is the principal axis. Okay, so we are now ready to go to the ray diagram. So again, before we proceed on the ray diagram that we have right here, you can pause this video several times if you want to. Alright, you can pause this video several times if you want to draw the image, to draw the setup, and to draw the lines that is needed for the ray diagram. Alright, so a ray diagram is a pictorial representation of how the light travels to form an image in a mirror or lens. Alright, in a mirror or lens, and tell you the characteristic of this image. Okay, now with the use of the ray diagram, you should be able to see how the light interacts in your optical devices like mirror and lenses. So let's get started. Okay, so we have here the principal axis. So the first thing that we will do is the concave mirror. Alright, so this is a concave mirror, and we have the center of curvature and the focus and the object. Okay, so I have here a certain measurement. For example, the center of curvature that I have right here is 10 centimeter, and the focus that I have right here is 5 centimeters. So you can use the same example as well. Okay, so you can pause this video if you want to draw this one. Okay, so rule number 1. Okay, so the first ray that we will going to draw should be starting from the top of the object, parallel to the principal axis, then through the F, which is the focal point after reflection. So how does it work? How does it looks like? Okay, again, you can pause this video. You can pause this video to draw this one. Alright, so now let's start first with the ray that comes from the top of the object parallel to the principal axis. So it looks like this. Okay, so it looks like this. Then, after that, it will be reflected, according to the statement here, it will be reflected through F to the focal point. Okay, through the focal point after reflection. So it looks like this. Alright, so did you get the right figure? Okay, did you get the right figure? So if so, then that is good for you guys. Alright, so okay, so this is the first line that we will going to have in our ray diagram. So we call this line as the principal ray. Alright, so principal ray. So always remember, principal ray goes to principal axis to focal point, P to F. Alright, so always remember this pattern. It goes from P to F. Alright, so principal axis to focal point. Okay, so that was the first ray diagram or line that we will going to use on the ray diagram. Next, let's go to the second one. Again, you can pause this video. Alright, so you try to attempt. Alright, try to draw the second line that we have right here. Okay. Alright, so for the second line, draw a ray starting from the top of the object through the focal point, then parallel to the principal axis after reflection. Okay, so how does it look like? Okay, first one, draw a line from the top of the object through the focal point. Okay, there you have it. Okay, so through the focal point. Then the next one is parallel to the principal axis. Okay, so we have here parallel to the principal axis. There you go. Okay, so what do you notice? Okay, so there are two lines that are intersecting already. Okay, so this line is called, so the green line that we have drawn is called the focal ray. So we have it earlier, the principal ray. This one is the focal ray. Now the pattern should always be going to focal point to the principal axis. So it should always go to the focal point down to the principal axis. Always remember that pattern. Alright, so there are already two intersected rays that you have right here. Okay, so before we move to the third line that we have, did we follow the law of reflection in this process? Do you think, okay, do you think we follow the law of reflection? Okay, so you write your answer in the comment section of this video below. Alright, so the answer is we did follow the law of reflection. Okay, we did follow the law of reflection. So this is the surface. Alright, so this will be the surface, and this is how the normal line looks like. Okay, so this is how the normal line looks like, and it looks like this. So therefore, we still follow the law of reflection. We did not violated any principle in the process. Okay, in this case, we have here the surface, and we have here the normal line. Okay, still they have the same angle of incidence, and then this is the angle of incidence, and then the angle of reflection. All right, so that is the second line. Let's go now to the third line. All right, so the third line is somehow this is somehow optional. Okay, this is somehow optional. As long that you have your first two lines that you have earlier, it's okay. Okay, if you have this, if you want to have this third line, it's okay. Okay, this is just optional. There are some situations where you cannot draw the third line. All right, but in this case that we have right here, we can draw the third line. Okay, so again, this is optional, only for mirrors. All right, so this is optional, only for mirrors. All right, mirrors only. Now, what is this third line? All right, so what is this third line? Draw a ray starting from the top of the object through C, then back upon itself. So it looks like this. Okay, so we have here the incident ray. We have here the incident ray, then it will be reflected. There you go. Okay, so now what do you call that ray? I called it C ray because it goes to the center of curvature. So for me to be easily remembered, I just use mnemonic called C ray. All right, so C ray. So that is the ray that we have drawn. That's the third line that we have drawn. So as you can see, what do you notice about the three lines? Okay, so if you said they intersect, okay, so if you said that the three lines intersect, then you are correct. Okay, what does this intersected line means? All right, what does this intersected lines that you have right here means? All right, what does it mean? Okay, so if you said that that is the location of the image, then you are also again correct, because the intersected line means that that is the location of the image. All right, again, the intersected lines that you have right here are all coming from the top of the object. Are all coming from the top of the object. So if we draw the image, it looks like this. Okay, so it looks like this. This is now your image. Okay, again, this is the top of the object, similar to the top of the original object that you have right here. Yeah, so that is the image. Now let's answer this following question. Okay, now is the image same or opposite side relative to the object? Okay, now to answer this one, every time that you will do a ray diagram, always, all right, for the image of the ray diagram that you have, every time that you are doing the ray diagram, don't forget the lost of the image. All right, so what do you mean by the lost? All right, what do you mean by this word lost? Lost, L means location. All right, location of the image. All right, we are talking about the image here. Next one, we have here the O, which is the orientation. All right, so there are two orientations of the image: upside down, all right, or inverted, or upright. So there are two: inverted or upright. All right, next one. The size of the image is the letter S. All right, so that's the size of the image. So there are three sizes that you should take note of. There are three sizes that you should take note of. Number one is same size. Number two is reduced. Number three is enlarged. Again, same size, reduced, enlarged. And finally, we have the type of image. The type of image, we have two types. We have real image and virtual image. All right, so there's no nothing in between. All right, so there's no more than that. Okay, now the type of image depends on orientation. Alright? If the orientation is upright, therefore the image is virtual. As we agreed on the previous videos that we had. Next one, if the image is inverted, then therefore the type of image is real. Okay, so that's the key idea here. Okay, so let's have this one. Okay, is the image the same side or opposite side of the object? All right, so same side of the mirror as the object. The answer is, based on this ray diagram, it should be the same side. So if it is the same side, therefore that is real. All right, so that is real image. Next one, is the image enlarged or reduced? So as you can see here, it is reduced to its original size. So that is your size, reduced. Next one. Okay, is the image inverted or right side up? All right, so is the image inverted right or right side up? So the answer is inverted. So as you can see on the image, as you can see on your ray diagram, it is inverted. So that is inverted. Now, in terms of location, where is the image located? Based on this one, the image is located in between C and F. All right. So can we write that one? Yes. We can write that one. So between C and F. All right. So there you have it. Okay. So that is your loss. Location of the image, orientation, size, and type of image. All right. So let's go now. So that was the ray diagram for concave mirror. All right. Next one. Example of concave mirrors are the following. So we have the satellite dish. So the receiver of your satellite dish that we have right here is the focal point of the mirror that you have right here, the concave mirror that you have over here. Okay? Instead of being a mirror, it is the radio waves that are being reflected down to this focal point. So this is the focal point where the receiver is located. Okay, so focal point. The radio waves or microwaves are being reflected to this area. Okay, and down to your television, and you can see now the programs that you are watching. All right. So whether the microwaves approach from this side, it goes to the same focal point. All right. So on this side, it goes again to the same focal point. Okay. Next, another application of concave mirror is solar cooker or solar fire starter. Okay, so we have here the solar fire starter. So in case that you are on a survival mode in forest, in a survival process, if you don't have any matches, with the use of sunlight, you can burn a combustible material using this solar fire starter. Okay, so this is a parabolic mirror. Okay, a concave one. Okay. All right, so let's go now to its opposite, which is the convex mirror. All right, so are you ready, guys? Again, you can pause this video. All right, you can pause this video several times for you to experience how to do the ray diagram. Okay. Okay, so we have here the convex mirror and the object. There you have it. Okay, so if you notice, the reflective side on the convex mirror is on this side. This is the reflective side. Okay, so this is the reflective side. So therefore, if the arc is going from the inside, then therefore, the focal point and then the center of curvature is on the inside as well. Okay? Yan. So, the focal point and the center of curvature must be towards the inside. Because the arc is from the inside. Okay, so this is your arc over here. So that is why no focal point. There are no focal point and center of curvature located on this side of the object. Okay, so anyway, you can place the object near the mirror or far away from the mirror, and you try to do the ray diagram for it. Okay, so in this case, let's start with the step 1. Again, you can pause this video if you want to. Okay, so for you to learn how to do the ray diagram. First one, draw the ray starting from the top of the object parallel to the principal axis. Again, the first ray that we have right here is the principal ray. Principal axis going to focal point. Okay, so it must reflect to the surface of the mirror after that, and draw a broken line that goes through the focal point. Okay, so in this case, since it is curved outward, all right, so the mirror is curved outward, then it will be reflected outward. Unlike your concave mirror that we have earlier. Okay, unlike your concave mirror. So, what will happen here? Okay, what will happen here? If your eyes are located here, so the tendency is your eyes will follow where this reflected ray coming from. All right, so this is the reflected ray. And this is your incident ray. So your eyes will follow where the reflected ray is coming from until it goes inside or behind the mirror. So, because of that, we will put a broken line behind the mirror. Okay, following your reflected ray. Okay, following your reflected ray that you have right here. So this is the broken line, and we satisfy the first step. It should go to the focal point. So as you can see here, the broken line goes to the focal point. Okay, so that is the principal ray for the convex mirror. Okay, so did you get the right figure? Okay, so did you get the right figure? So if so, just comment it down on the comment section. Alright, so next. Alright, so for the second line, so draw a line. So this is the focal ray. Remember, focal ray is focal point to principal ray. Alright, so focal point F to P. Alright, so draw a ray starting from top of the object through the focal point. Then it will reflect to the mirror. Continue the reflected ray with the broken lines on the other side of the mirror. Okay, so how does it look like? Again, you can pause this one. Okay, so assume that it will go to the focal point. Okay, so assume that it will go to the focal point, but it's not, because it will be reflected. Okay, so did we follow the rule? Did we follow the step? Yes. Focal point, then parallel to the principal axis. Now, what will be the problem here? Alright, again, your eyes are located here. Alright, so again, your eyes are located here. So, this is the reflected ray. This is the incident ray. So, therefore, your eyes will follow the reflected ray. Alright, so as it follows the reflected ray, it will create an imaginary line behind the mirror. It will create an imaginary line behind the mirror. So, what will happen is, it will continue the reflected ray towards the back side of the mirror. So, we have now your broken line over here. Alright, so, again, rule of thumb, the broken line must be the continuation of the reflected ray, not the incident ray. Okay? Not the incident ray. Now, if you use the incident ray to draw a broken line, you will be in a world of trouble. Okay? You will be in a world of trouble. Alright, so that is the second line called the focal ray in a convex mirror. Alright, so the third line, if you want to draw the third line, it looks like this. So, this is the incident ray. Alright, so that is the incident ray. And we have now the reflected ray. So, as you can see, this arrowhead. Okay, now, so because it will be reflected, your eyes again will follow the reflected ray as if it comes from behind the mirror. Okay, again, the third line is still optional, guys. Please remember, the third line is optional. Okay, you can have the first two lines. Okay. To form the image that you will have right here. Alright, so what is the image looks like? So the image looks like this. So did you get the right image? Alright, so did you get the right image? So did we get both the right figure? Okay, so if so, then that is good for you. Congratulations. Alright, so let's answer. Okay, again, don't forget, every time that you draw a ray diagram, you still have the lost. Okay, for the image. Okay, let's start first with number 1. So, is the image on the same side or opposite side of the mirror relative to the object? So, as you can see here, this is opposite side. So, therefore, this is a virtual image. This is a virtual image. Next one, is the image enlarged or reduced? So as you can see, the image is reduced completely to its original size. So this is reduced. That is the size. Next one, how about number 3? Is the image inverted or upright? So as you can see, okay, logically speaking, that is upright. Okay. Now, what will be the location? Okay, what will be the location? So, you can write here the location of the object in our ray diagram. You can write here in front of F. Right? You can write it like that. Or, you can have it behind the lens or behind the mirror. Why behind the mirror? Because the image is formed opposite to the relative object. Alright? The image is formed opposite side of the relative to your object that you have right there. Okay? So, that's the reason why we can answer behind the mirror as your location. Alright? So, that was your convex mirror ray diagram. Okay? So, what are the example of convex mirror? So, we have it right here. You can see this one on blind curves. Okay, you can see this one on roads with blind curves. Alright, so you can see this one. So, this is a type of a convex mirror. Also, the side mirror of cars, it is also a convex mirror. As you can see, there is a statement there that says that the object seems near. Alright, the object seems near on the mirror. So, which means that in reality, the object is far, but on the mirror, it looks near. Okay, it looks near, but in reality, that is the object is far away from you. Okay, so that is a convex mirror that we have right here, the side mirror. And aside from that, convex mirror is also used in dentistry. You know the device that is used by the dentist, which has a mirror on it. Alright, so device that looks like that. The mirror is on this side, and the dentist puts this one inside our mouth to better view the teeth on top of your jaw. Okay, so on the top, yeah. Okay, so that is the convex mirror. All right. So with that, so this is the ray diagram for concave and convex mirror. You can form any variation of this one. Okay, you can place any point or any location of the object and try to do it differently from the one that I have right here as an example. You can place the object between C and F. You can place the object on C. You can place the object in front of F. So, you can try different variation and try to find out whether the image is the same all throughout or not. Okay, so this is the concave and convex mirror. And that was your concave and convex mirror. Alright, so before we go to the next optical device, so I'll just introduce you first to the process in which this optical device follows. Okay, so this principle is also known as the Snell's law of refraction. Alright, so we all know that refraction is the bending of light when it passes through two materials with two refractive indices. Okay, so what does the law of refraction tells us? Okay, in our previous lesson, it tells us that it is used to describe the relationship between angle of incidence and angle of refraction of two materials with two different refractive indices. Alright, so it works on two materials with two refractive indices. Otherwise, if the material has one refractive indices If the two materials has one refractive indices, it will be useless. Okay? So it will be impossible for the refraction to occur. Again, they have the normal line. Okay? The normal line is the basis. Alright? It is the basis where your angle of incidence and angle of refraction will be counted or will be measured. Alright? So this is the formula, alright, that we have discussed before. And fortunate enough, we will not follow this formula here. Alright, we will not use this formula here. Okay, in our ray diagram. Alright, so that was Snell's law of refraction. Okay, so what are these two optical devices? What are these optical devices that uses the refraction? Alright, so if you guess it, okay, if you try to guess it, well, you guess it right. That is lenses. So we have here spherical lenses. Okay, so we have the concave and convex lens. So other books or other reference uses biconcave lens, or we have biconvex lens. Okay, it's the same thing. Okay, convex lens are also known as converging lens. Alright, concave lens also known as diverging lens. They diverge light, they converge light in the process. Alright, now in terms of application, prescription glasses uses lens. Prescription glasses to treat farsightedness and nearsightedness. For example, if you are farsighted, okay, if you are farsighted, you might want to use convex lens to correct that eye problem that you have. Okay, convex lens are for farsightedness. Okay, next one, if you are nearsighted, all right, if you are nearsighted, the lens that used to correct nearsightedness is called the concave lens. So this is the for nearsighted. Okay, so because the lens in our eyes, is convex lens. Okay, just a trivia guys, just a trivia. The lens in our eyes is a concave lens, or convex rather. All right, so this is our eye lens. Okay, so whether you have a farsighted or nearsighted problem, what part of the eye has a specific problem on that? The lens on your eyes. Okay, the lens. Okay, on your eye that you have right there. Okay, so in order to correct that one, ophthalmologist will will prescribe you a convex lens if you are farsighted, concave lens if you are nearsighted. All right, so that is the idea there. All right, so we have here the lenses. As you can see here, it is completely different from a mirror, but it has the same parts. It has center of curvature. It has focal point. But the thing is, instead of having one center of curvature, it has two. Why do you think it has two center of curvature? So you put it in the comment section below. Okay, why do you think that we have two center of curvature here in our lenses? All right, so the answer there is because it has two arcs or two curves or two circles. Okay, because the lenses that we have right here has two circles or two arcs or two curves, that is why it has two centers. Okay, for example, this center of curvature that you have right here, or 2F, all right, so the 2F that you have right here is from this arc. Okay, is from this circle that you have right here, or arc. Next one, this 2F that you have right here is from this arc. Okay, so that is why we have two center of curvature. Okay, next one, this diverging lens. The center of curvature here is coming from this arc, and the center of curvature here is coming from this arc as well. Okay, so we have two arcs that you have. So that is why we have two center of curvature. Now, if you have two center of curvature, automatically you have two focal point. All right, each half the distance of the center of curvature. It's the same thing. It is half the distance. So if you follow this formula right here, okay, so if you follow this formula over here, right, if you follow this formula, then it's the same thing. Okay, again, we have the principal axis. Okay, again, we have the principal axis. So there, that's the converging lens and the diverging lens parts. Okay, so we go now to the ray diagram. Okay, so again, you can pause this one. You can pause this video several times for you to experience how to draw the ray diagram. Follow the rule that we have right here. Okay, so you can draw this one before I reveal the answer. Okay, so this is the convex lens. Okay, the principal axis, and I have here a vertical line drawn at the middle of the convex lens. And there you have your points, which is the 2F, F, and okay, so for you not to be confused on the F and the 2F on the other side, I put here an apostrophe, which is called as F prime and 2F prime. Now, if you want this one written as C, it's fine. All right, it's fine with me. Okay, so if you want to be have it written as C, okay, you just put it prime. Okay, so C prime. Okay, so to indicate that it is on this side. All right, so there's your object. Okay, so you can pause this video and you can draw this one. Okay, now again, in making a ray diagram, you should start first with principal ray. That is a ray, that is the light ray that goes from principal axis to focal point, P to F, and followed by focal ray. All right, focal point to principal axis. All right, so let's start first with the principal ray. So draw a ray starting from the top of the object parallel to the principal axis through the F prime. All right, remember, through the F prime, not the F only. All right, not the F, but the F prime after refraction. All right, so where will it go? So starting from the principal axis parallel, then it goes to the F prime. All right, it goes to the F prime. Okay, now what happens here is the light is being refracted. All right, remember, okay, so this is air and this is glass. Remember that glass, all right, remember that glass has higher index of refraction than than your air, rather. All right, so since your air has lower index of refraction and the glass has higher index of refraction, the light will bend towards the normal line. All right, the angle of refraction will go towards the normal line. So that is why the light rays that you have right here, this light ray that you have right here, looks like that. It's because air has less index of refraction than glass. Okay, so that is your first line, which is the principal ray. Okay, that's the principal ray. All right, next, let's go to the second line, which is the focal ray. Again, okay, so earlier we have the principal ray and it looks like that. Okay, so how does a focal ray, or what is a focal ray looks like? Okay, so in a convex lens. Okay, so draw a ray starting from the top of the object, passing to F and parallel through the principal axis. Again, you can pause this video, okay, to try it out. So, how does it look like? So first, it goes to the focal length or focal point, not the prime one, not the prime, but the focal point without prime. All right, without prime. Then, it goes parallel to the principal axis. It goes parallel to the principal axis. So, it looks like that. Okay? Again, you see some intersected lines. So, it gives you an idea that the location of the image should be right here. Okay? So, hold your horses first. Alright? So, we have the third line. Alright, so the third line. So, again, we have the object, principal ray, and the focal ray. Now, the third line is the optical ray. So, the third line is the optical ray. So, the optical ray, according to the step, draw a ray starting from the top of the object, passing through the optical center of the lens. Okay, so you can pause this video to try out to draw it first before I reveal the answer. Alright, so what does the optical ray look like? How does it look like? It looks like this. Alright, so this is your optical center. Alright, so this is the optical center. Now, why is it that the light is why is it that the light is not bent on optical center? All right? Because the optical center is a huge chunk of square block of glass. As we all know, square shaped prism, all right? Square shaped prism doesn't bend light. All right? Square shaped prism doesn't bend light. So this is a square shaped prism, so it doesn't bend light. So that is the reason why any light that goes from the optical center remains undeviated. Okay? So remains undeviated. So that is the optical ray. So we called it the optical ray. Okay. Now, every ray diagram that we solve, we usually have the lost. Okay? Now, what is the image looks like? Okay? You can draw the image now. Okay? You can pause this one and draw the image before I reveal the answer. Alright? So, let me see if you are correct. Okay, so did you get the correct image? Okay, so you can respond in the comment section. Okay, so if you get the right image, then we can get the lost. Okay, so first one, is the image enlarged or reduced? Okay, so is the image enlarged or reduced? So the image is reduced. Okay, so as you can see, all right, so that is reduced. So that is the size reduced. Next one, is the image inverted or right side up? Okay, as you can see on the picture or the ray diagram that you have, the image is inverted. Okay, so if the image is inverted, then automatically that is a real image. Okay, now where is your eye located? Your eye is located somewhere here. Okay. Okay. Now, in terms of location, what is the location of the image? Alright, so what is the location of the image? So, the location of the image is between F prime and C prime, as the drawing stated. Alright, as this ray diagram stated. It is located between F prime and C prime, respectively. Okay. So, that is the lost. Okay, so that is the image lost for convex lens. And that is the ray diagram for it. Okay, so, next one. Okay, so that was the convex lens. We go now to the concave lens. Alright, so again, you can, you feel free to post this video anytime that you want. Alright, so this is a concave lens. And the principal axis, and the points, the F prime, the 2F, the 2F prime, and the object. Alright, now the problem here is how to do this one. Alright, so you can draw this one first on your own. You can pause this video. Alright, so the first thing is the same one, principal ray. Draw a ray starting from the top of the object parallel to the principal axis that will go to F using broken lines after being refracted. Alright, so after being refracted. So, it looks like this. Okay, so parallel. Then, where will the refracted light go? Where will the refracted light go? Again, refracted light, not reflected light. Okay? Now, where will the refracted light go? Is it on the F over here or the F prime? Okay, so let's take a look. So, as you can see here, the thicker part of your concave lens is on the top. So, meaning to say, it will likely to be deviated, alright? It will likely to be deviated towards the normal line. Alright? It will likely to be deviated towards the normal line, and because of this angle that you have right here, right? So because of the angle that you have right here, so if that is the angle, so this is your normal line, alright? So this is your normal line right here. Then the angle of refraction, the angle of refraction will be going right there. Okay? It goes right there. Okay, so now I will remove the sketches. So it looks like that. So the next one. So according to this one, broken lines after being refracted. So, it doesn't go to the F prime. It doesn't go to the F prime. Instead, it goes to the focal point over here. So, using the broken lines, we can continue the refracted. This is the refracted ray. Alright, this is the incident ray. Okay, so we can continue the refracted ray using the broken lines that we have right here and landing it on the focal point over here. Okay, now, what is the broken line means? What does the broken line mean? It means that the eyes, okay, your eyes is following the refracted ray until to the point right here. It follows the refracted ray. It follows the refracted ray and it forms an imaginary line on this side. Alright? It forms an imaginary line on this side. So what happens is, it forms this broken line over here. Because of our eyes. Okay? So, next one. Okay, after the principal ray, obviously, we have the focal ray. Okay, again, same thing. There you go. And there you have it. Okay, so, rule number 2. Again, you can pause this video. Alright, rule number 2 or step number 2. Draw a ray starting from the top of the object that goes to F prime. But it will be continued by broken lines after being refracted parallel to the principal axis. Alright? Parallel to the principal axis. So, what does it mean? Okay, it looks like this. So, draw, okay, just like your focal ray, it goes from F to P. Okay? But this time, it goes to the F prime. Like so. But, since it will be refracted, it will not go to the F prime. Instead, it will go parallel to the principal axis. So, what happens here? It is diverging or it diverges the light. Alright, in the process. This concave lens diverges the light rays that we have. So, if your eyes are over here, then therefore, your eyes will follow this refracted ray. Alright, so your eyes will follow this refracted ray and form a broken line on the other side of the lens. Okay? It will form a broken line on the other side of the lens. So as you can see here, there's already an intersection. There is an intersection already in the process. Alright, now, okay, let's go now to the third line. So we have now the principal ray. Then we have now the focal ray. And the third line is the optical ray. Alright. Now, in some cases, you can draw the optical line. And there are some cases that you cannot draw the optical line or optical ray. It's okay. Because as long that you have these two rays that you have right here, as long that you have these two rays that you have, it's more than enough. Alright, to form the image. Alright. So, this is the optical ray. It goes to the optical center. Okay? Okay, you can pause this video if you want to draw the image. So, draw the image. Alright, so draw the image. So, do we have the same image as what I have right here? Okay, so if so, then you comment something on the comment section. Okay, if you got it correctly. Okay, so the image is something like this. Okay? So, again, every time that we draw a ray diagram, we always use the loss. Okay. Let's start first with the first question. Is the image enlarged or reduced? As you can see, it is reduced. Okay, so that is the size of your image, reduced. Next one. Is the image inverted or right side up? What do you think? It is upright or right side up. Okay, so that is upright. So, if that is upright, then therefore, the type of image that we are dealing here is virtual image. So, this thing is a virtual image. Right? So, that is a virtual image. Now, in terms of location, what can we write about the location? We can say that the location is in front of, we can have it in front of F. Alright. That is also that is correct. Now, you can have it behind the lens. Why is it behind the lens? Because relative to your eyes, this image looks like it is coming behind the lens. Okay, relative to your eyes. Okay, relative to your eye right here. Okay, so instead of using in front of F, you can have also behind the lens. Behind the lens. Okay, so in location of the image. Alright, so there you have it. The concave lens. Okay, so with that, let's have the application of your concave lens. Alright, and your lenses. Not only the concave but also the convex. Now, convex lenses can be seen on magnifying glass. Alright, so it is used to enlarge an image. Now, the question is, I want you to make a ray diagram that uses a convex lens that enlarges the image. Alright? Not only that enlarges the image is also upright. Okay? The image is also virtual. Is that possible? Okay, so if you want that, draw the ray diagram on that, and then let me know in the comment section what is if it is possible or not. Okay, again, using a convex lens. Okay, using a convex lens, is it possible to produce a virtual image using a convex lens? If so, write it down in the comment section if it is possible. If it is not, why not? All right, so next one, microscope uses convex lens. All right, microscope, the lenses that you have on your eyepiece and the objectives that you have right here, and the diaphragm. All right, the diaphragm over here uses convex lenses. All right, next one, spy hole doors. Remember, if you watch a movie, something like someone is, if you want to know who is knocking on your door on the other side, there is a spy lens. All right, there's a spy lens that you have right here in which you can look whoever is on the other side of the door. All right, again, this is a concave lens, so that is why the person on the other side is upright. All right, upright. Next one, flashlight. Okay, so why do you think flashlight uses concave lens? Why do you think concave lens is very important in flashlight? Okay, so you write your answer in the comment section. Okay, let me know your answer. So flashlight uses concave lens. It's because if you want to disperse light on a larger area, if you want to disperse the light on the larger area, concave lens is a very good type of lens to use in that case. All right, for flashlight. All right, if you want to disperse the light. Okay, so that is your examples of concave and convex lenses. All right, so okay, there's another type of lens called Frsenel lens. Actually, this Frsenel lens is just a modification of concave lens. This is just a modification of concave lens. So instead of having a concave or convex surface, rather concave, convex. Okay, sorry for that. It is convex. All right, convex. So instead of having a convex surface that you have right here, okay, in order to make a Frsenel lens, you will make a ridges out of that convex surface. All right, so out of that convex surface. So what's the purpose of this? Now, if you happen to see a lighthouse, the light coming from a lighthouse is beamed at one focus. Okay? It is beamed, the light from the lighthouse is beamed at one focus. So how does it work? How is it even possible? Now, if you have a convex lens, okay, if you have a convex lens that like what you have right here, the light is likely to be scattered. All right? The light is likely to be dispersed. Now, if you put ridges on a convex lens, then the light now will not be dispersed. It will follow a certain path, a straight path. So therefore, your light now is beamed at a certain focus. Okay? At one focus. Okay? So, this is what the Fresnel lens looks like on the lighthouse. All right, so this is the light from the lighthouse. All right, so the one that you have right here, the old projectors, overhead projectors, uses Fresnel lens. Okay, so there is also a technology called invisibility shield. All right, so let's watch this video. Okay, so this is the video. So I will put the link in the description of the video below. Okay, so for you to watch that this one at your own at your own time. All right, so that is the invisibility shield. So as you can see here, all right, so as you can see here, this invisibility shield that you have right here is an example of Fresnel lens. Okay, now this particular Fresnel lens has a microscopic ridges. All right, it has a microscopic ridges on the surface of this lens. So that is why it affects how light passes on this lens. Okay, so as you can see here, the pliers are invisible but the sticks are not. Okay, we can assume that the ridges are horizontally, all right, the ridges are horizontally made like the one that you have right here, because you can see the wooden sticks that you have on the other side but not the pliers. All right, now in order to see the pliers, you need to change the orientation of the lens. You need to change the orientation of the lens to do that. So at this time, you can now see the pliers but not the wooden sticks that you have right there. So meaning to say that the orientation of the ridges affects how light passes from one side to the other. Okay, so this is an example of a Fresnel lens. All right, so
of the pliers shining through this lens, and suddenly these parallel sticks have disappeared. Now I turn it back the other way, and there they are. They reappear. Now,
all right, so changing the direction or changing the orientation of the lens affects how light affects the direction of light passes through this lens. Now, who knows? In the future, we will have a technology called invisible cloak that utilizes the idea of Fresnel lens. Okay, so with that, all right, so with that, that is the Fresnel lens. Okay, so all right, so in order to summarize our the things that we have encountered this video lesson, so the first one, there are two kinds of spherical mirrors. So we have convex and concave mirrors. All right, so concave. All right, concave mirrors are curved inwards, while convex are curved outwards. All right, so next one. We have two kinds of lenses. So we have converging lens and we have the diverging lens. Okay, so the converging lens looks like this one, and the diverging lens looks like this one. All right, so next one. Mirror and lenses has the following parts. Number one, focal length. This is the distance. All right, so this is the distance in the pole of the mirror to the focal point. All right, or in the optical center or the surface of the lens to the focal point. That is the focal length. Okay, next one, the focal point is the half distance of your center of curvature. Okay, so the center of curvature is obtained using this formula, C is equal to 2F. And the focal point is obtained by dividing the center of curvature by half. Okay, so next one. Okay, there are steps in doing ray diagram. So the first one is the principal ray. Draw a ray parallel to the principal axis down to the focal point. Then followed by the focal ray. So the focal ray is the ray that goes to the focal point parallel to the principal axis. And we have for mirrors only, we have the C ray. This is optional. Okay, that goes to the center of curvature. And the other ray for the lens is called the optical ray. Again, this is optional. Okay, it varies on the situation in which you can draw these third rays that we have right there. So we called it the optical ray, and that is for lens only. All right. So when all rays intersect, that is where the image is formed and located. Okay, so with that one, guys, all right, so that ends up our video lesson once again. And if you learned something from this video, you can leave a like. Okay, you can hit the like button of this video, and you can subscribe to my channel for more videos, science videos. Okay, for you to be updated with more science videos in the future. Now, if you do have question, if you do have suggestion, you can write down in the comment section below this video. It will help me a lot in the algorithm in this YouTube channel. So please leave a like and subscribe to my channel. So that's it, guys. Let's see each other next time in our another video lesson. So stay safe, everyone, and see you guys.
Bakaみたい子供なのね夢を追って傷ついて嘘が下手な